Hey, welcome everybody to DEF CON 1 Science, our fourth one. Now, I know we were supposed to do this every week. However, due to logistics, we're going to probably be doing it every other week. But we have a show to make up for the fact we weren't on for last Sunday or two. So today we're going to be discussing if the question is there, what happened before the Big Bang, a sensical question to ask. And we have a great lineup with us today. We have, of course, with us Landon, Curt, Noll, my co-host. Welcome back, Landon.
Hello.
We've got
Thank you. Good to be back. Good morning, good afternoon, or good evening, depending on your time zone and latitude.
And again, time zones are because the Earth isn't flat, right?
Yeah. Yes. Also, a special thing there is that I'm taking the YouTube feed and feeding it through the satellite. So the folks at AstroAthens and Scott are in a sunrise party, and hello to those folks there.
Hi.
So if you
That's great.
So hi to the South Pole.
And by the way, people remember, Landon actually called me from a Iridium sat phone from the South Pole, so it does exist. But we also got Dr. John Kroon with us. You guys remember him from his proto-planet discussion on the NonSequitur show. He's going to be doing another one, I think, next week. But he's with us today to talk about this particular topic. Welcome, Dr. Kroon.
Thank you for having me.
And you might recognize AstroAthens on the very left on my screen here. She is an international model and an amateur astronomer, and she has a great channel. I've recently just been exposed to her on Twitter and on YouTube, and I've been kind of binge watching. And one of the videos that I came across was on the no boundary proposal, and I thought she did such a stellar job on it. I was like, let's get her on and actually let's talk about that particular topic in this video. But I'm going to the link to her video channel is in the video description. So before you even introduce her and before she even says anything, go subscribe to her first. We got to get her at least a couple hundred subs out of this. So anyways,
yes,
Athena, welcome to our channel.
Woo! Thank you so much. Happy to be here. Very excited to talk about some stuff.
Got some coffee. And what is that in the background? What do you got there on the painting?
Falcon Heavy. Falcon Heavy. It's really great photo, actually.
Awesome.
Yeah. Taken by Ryan, also known as Space Tripper, or Science Tripper, actually, on Instagram. But yeah, he took that himself. It's really cool. 17-year-olds.
The first time I ever saw one of the Falcon 9s, I honestly thought it was CGI. I really did. I'm not gonna lie. I was like, this can't be real. But that's
it looks like
just
so good.
It's amazing, the technology, isn't it? I mean, we've just come so far in our advancement and understanding of rocketry that have something like that can actually go vertical and come back vertical. And who would have thunk, right?
Yeah,
that's awesome.
Yeah, exactly. That could be a nice giant poster in my bedroom.
So we are waiting for Kyle. Unfortunately, Kyle hasn't showed up yet, but we did let him know we're going to start. We are dual streaming. This is a first for us. We're actually streaming to my channel and in the NonSequitur channel. So hopefully you can join us from either one of them.
Welcome on which channel you're on. Yes. Welcome
Either
to
one,
which.
pick one. Yes, Dave. What's the matter? Okay.
Oh.
Okay. That explains why he
dear.
can't join us. Hopefully he's okay. Okay.
Well, it's the
unfortunate turn
problem
of
that the
events.
electrons of his car were excessively repelling the electrons of the other car.
Mhm.
Due to the Pauli exclusion principle, they could not be at the
It's
same
a
state at
dang
the same
Pauli.
time, and so
Yeah.
things went
What I tell you about Landon overthinking prior to the show? But that's why we love him. Because he knows what Pauli's exclusion principle is. Okay, so anyways, we're going to dive right into this. I'm going to ask you guys the question first to kind of get you guys' opinion on it. I'm going to kind of go through a presentation that I made. Landon has changed a couple slides, so I'll defer to him on those slides. But I'm going to give my argument why I think that the question, what happened before the Big Bang, is nonsensical. And unfortunately, Kyle can't join us to give his side because he thinks it is a sensible question. But we can't change the events that have happened. So Athena, I'm going to start with you because you are the new person to the channel. When I first got a hold of you and I asked you this question, you kind of gave me your opinion on it. But what do you think of the question? I mean, do you think that's a sensible question to ask? And if no, why not?
Well, I actually do think it's pretty sensible to ask, just because all of human history, we always want to try and ask why and what the reason is behind why certain things really go on, and then what can actually back it up. So as far as what happened before the Big Bang, it's something that, in all honesty, needs to be figured out, because there's so much debate about it right now. So as far as what actually went on before the Big Bang, there's a big question mark right now over all of it. So I do think that it is something that obviously needs to be pondered. But I think that, yeah, I mean, I believe you were actually going to give your opinion first, but I was going to actually branch off of what you were going to say. But yeah, it's definitely something that yeah, there's a lot right now that has to be said about. I'm ready to dive into.
All right, so she
I
thinks
think
that
it's
it's
a natural.
question.
Yeah, I think it's a natural question to ask. It may not be a sensible question to answer, but it's a natural. It's a common sense question to ask.
Okay, let's clarify. Let's clarify, because there might be some kind of disparity in the question formation. We do ask questions. People do ask questions all the time, but there are such things as nonsensical questions. My example would be, where do you find I on the real number line? It's sure you can ask that question, but it really makes no sense to do so. I think that this is a similar question. It makes no sense to ask. Well, that's the example that Hawking uses, right?
Yeah,
He uses that exact example. So I don't think that it's a sensible question to ask, even though we are allowed to ask certain questions. But does it make sense to do so? Dr. Kroon, what do you think?
Yeah, I mean, not to be a broken record, but I agree in the sense that it's not very, I guess, sensible, but we could learn a lot from it by asking it. We learn, we ponder a lot of deeply rooted aspects of the universe, of time, of space right now, and the moment of the Big Bang, and thinking about all of these things at a very advanced level can be extremely interesting, to say the least. So it's a worthwhile endeavor, even if the answer is no, nothing as we know it existed before the singularity of the Big Bang.
Okay, I think that's a fair way to put it. Yeah, I mean, we do have an inquisitive nature. We do want to know the answers of things, and we also want to know if it even makes sense to ask that kind of question. So, do you guys want to just like jump into this presentation that I sent, and then kind of go through each slide and give your evaluation of maybe the way Hawking takes his approach, the new no boundary proposal, to say, okay, can we at least model the universe in a way to get us to t equals 0, which would be, as we know it, the singularity event, right? That would be the start of everything, if there's going to be a start of some kind. Would you agree?
Yeah, I mean, I think part of the thing that we have to come up with is what happened at t equals 0. If we can determine that before you talk about, is there a negative t, and is the question relevant?
Yeah, exactly. And the way that they go about it, it requires a very sophisticated means of modeling using quantum mechanics, loop quantum gravity, and general relativity. And that's why I think that you even answer the question, certain things have to be kind of understood conceptually wise. It's not an easy question to ask or be answered even at time equals 0, which they're attempting to do. So what I kind of did was through this presentation, I just hit the high points of what I think that the average person would have to go learn about in order to try to understand what the no boundary proposal is and what it would take to model such a thing at t equals 0, or hypothetically before t equals 0, which would be the question, what happened before the Big Bang. So however, we just kind of dive into that, and then I'll be asking you three about each slide and what you think, and then we can kind of relate to the audience these kind of concepts. Sound good?
Yeah,
Sure.
let's do it.
Excellent.
Okay. All right, Dave, roll it. Roll it, roll it, roll it. All right, so this is going to be a trigger warning, just to get you guys prepared for this. This is going to be some major science. This is not like our typical, we're just going to be talking about some kind of superficial stuff. When we talk about science in the DEF CON 1 show, we kind of at least want to make it such that we don't want to water it down too much, but we do want to have the high points of the science, but we want to be able to explain it in a way that the audience understands it, because you guys are not idiots. You guys have had some basic science, and I think that you guys can probably understand everything that we're going to have in here, except for one or two things that even I don't understand. That's what Landon added. But anyways, it is the why the question of what happened for the Big Bang doesn't make sense. Okay, next slide. A little bit of an overview here. I'm going to be showing, using a little bit of math and physics, why the question, what happened before the Big Bang, is nonsensical. I'm going to be taking what's called a heuristic approach, meaning an approach that uses analogies and examples, but may not be exactly true, but in a way to be a pedagogical approach to teaching these concepts, because they are things that you're going to have to take 6 months to a year to even kind of begin to understand it. Even most of the things we're going to talk about, I don't have a very deep understanding. It's a very superficial understanding. But this is not something that's going to be something to get you through college physics, okay? I do suck at quantum mechanics. I'm not going to front. We didn't have to learn much quantum in nuke school. It was all just atomic physics. So most of what I learned about quantum, I had to do on my own, or I did take physics in college. But even then, they don't really get into the details of quantum mechanics unless you take an actual course in quantum mechanics. But I think most of the people I have here have a lot more education in this topic than I do. So, so I highly recommend what you
at some point. The nuke school is going to include fusion reactors, and then they'll have to learn quantum mechanics.
At some point, yeah, that's a good point. Right now, I mean, everything in the nuke school is all fission. It's all pressurized water reactors, not even boiling. So we're not even at boiling water reactors yet. But anyways, I recommend that you just take what we put out here and check with actual experts, even though they are actual experts in here. But somebody who's maybe specifically expertise in quantum mechanics and, well, cosmogony would be the correct term. Next slide. I had way too much coffee this morning. Can you tell? What is and is not the Big Bang? The Big Bang is not a theory of origin of the universe. I think we all agree upon that, right? I mean, would you guys say that a lot of people get that conceptually confused, that they think the Big Bang is how the universe began?
Yeah, absolutely.
And why do they do that?
Yeah.
Why do they think that for some reason the Big Bang is the origin of the universe and not the theory that explains the rapid inflation of the universe after the universe began? Why would you think people kind of make that mistake and inflate the two? Tina?
I think it probably has to do with the name itself, because when you hear this terminology of Big Bang, you initially think, okay, that involves some type of force and it involves some type of matter. So that means that had to have what started everything that we know in existence today. And then they don't, unless you actually break it down and look at the entire scale of going from like also the dark ages and then into inflation and then into when everything actually started to form and galaxies and stars formed, then you see, oh, wait a second, this isn't actually like what, like you said, isn't really actually the origin of the universe. It's more of just an event that happened very spontaneously and quickly. And that's probably where the misconception comes from. It's just because there's usually a general brush over, I think, a lot of times, especially when it comes to, I don't know, maybe like shows and stuff like that. When they talk about the Big Bang, they think, oh yeah, that's what initiated everything. And that's this is the origin of the universe. So that's probably, I think, why I get that a lot from people, because they think, oh, well, the name, it just says Big Bang, and that's usually what starts anything, as opposed to looking at it as a thing that actually what was a moment, a point in time that initiated a growth after that. So that's
So it's
kind of my viewpoint.
Just a misnomer in some ways, right?
Yeah.
Well, remember that the Big Bang term was was originally coined by Fred Hoyle on a radio program to derive, basically as a mocking the theory, right? There was
right.
People were using terms like primeval atom or primeval nucleation or something of that form, and Hoyle sort of said, well, it sounds like they're trying to describe a Big Bang, right? And that was meant to sort of mock the thing, but that moniker kind of stuck, and so we talk about Big Bang cosmology.
Do you think the name will ever change? Like even generations in the future, a century later, it'll be have a better name?
Yeah, I personally do, because honestly, if they relate quantum mechanics to like general relativity, there's going to be something newer and bigger and better that comes out of these theories.
Yeah, I remember
you,
Brian Cox called it a everywhere expansion.
Everywhere expansion.
But again,
yes, that's a good one. Yeah.
So the theory talks about that our universe began in a Higgs dense state, and it's still expanding after its initial event, and the matter of the universe is approximately 80% hydrogen, 90% helium, 1% lithium, blah blah blah. It states things like that, but it talks about how the universe began, not what was there beforehand. But theories don't need to explain everything, right?
Right, and that's a good point. Even within the Big Bang theory, there are other theories to explain things, which we'll be getting into.
Mm-hmm.
All right, so the Big Bang basically explains the inflation of space-time, basically. Next slide. And by the way, don't forget, people, go sub to Athena while we're waiting for this. I want to see those numbers kind of go up, people. Okay, because in the video description, you can go to her link. Come on. We got like 200 people that can go right now and do it. So
I write out the
Big Bang and
function.
inflation. Yeah, I'm not kidding. Go check out her videos. I mean, you guys are gonna be impressed. So anybody can talk about wave function, you should be automatically a sub to. So this is where we start getting into the actual science, Big Bang and inflation, because if you look to the right, the Big Bang will show various epochs of time from the point of whatever it was where the universe began, where this hot, like you said, this hot, dense universe started cooling off, and you started having things like recombination periods where all these ionizations would allow for atoms to start being neutralized by protons absorbing taking electrons and making neutral atoms. This reionization is the opposite of ionization. And then obviously, they had matter forming, but you also had things like the quarks being formed and this gluonic soup and all this other stuff. But the main thing is that there was a period of time that was very, very short. I think it was around 10 to the negative 32 seconds, if I'm not mistaken, the inflation period. Somewhere around that ballpark.
It depends on that's one of the things that people are trying to determine, pin down, is when the inflation period started and stopped. But one of the important things to note, and it was mentioned also in the chat, is that the Big Bang starts out with a non-inflating universe, right? Inflation comes later. The Big Bang event, and then you get inflation, and then inflation stops or slows down.
Right.
Most Big Bang models that have inflation start with a Big Bang and then bring in inflation, and then inflation turns off.
So what was the main reason why they came up with the inflationary model in the begin with? I have 3 different reasons, which we'll get into, which was obviously the cosmic horizon problem, the monopole problem, and the flatness problem. But why did we need to actually come up with something to explain these things away?
Well, okay, I'll jump in. One thing is that you see kind a funnel happening here, and that's something that right now has been a way to sort of explain what we see currently happening in the universe. So coming from an observational standpoint, where we weren't around when the Big Bang happened, but we are around now, and we see everything around us moving away at an accelerated rate known as the Hubble constant. And so you see this constant expansion. So if you were to go backwards and rewind that, like as if you're rewinding obviously just ourselves, then you'll start to see that obviously this is where right now we're in expansion, but that had to have retracted, and then you keep getting smaller until you get to the Big Bang. So for me, this is kind of a basic way to sort of explain that. I know someone can go into more of an elaborate way, like you said, bringing up the other models, but that's really where inflation came in, because it serves as a funnel to explain to the point that we're at today and then where we're going.
One of the things that happened early on with the history of this theory is that the assumption was that the theory states that the universe began with a hot, dense, uniform state. And the question that was asked is, well, how did it get to this non-uniform, lumpy universe that we have today? And they began to run into problems if they assumed that things just magically decided to clump up, because in that early universe, the universe was able to equalize. So if there was any fluctuation that caused some part of the universe to get hotter, the energy was quickly dissipated throughout the rest of the universe. The universe was compact enough that things could equalize, and then, but that's not the case today. And so inflation was an attempt to try to take Big Bang cosmology and actually put it on a sound footing with respect to the observations that we see today. Work is going on right now at the South Pole. There was an initial attempt with something called BICEP2 that was looking at, supposedly, they're looking for evidence of the effects of the in inflation state. And there were some problems with the data. In particular, there's some stuff that they couldn't rule out with regards to dust complicating their measurements. So BICEP3 is being conducted right now, where they're using a multi-wavelength set of measurements. And when I was there in January, the people were very pleased with the performance of the instrument. Obviously, they're not going to reveal the data that they're collecting, but they say that the instrument is working well, and they're expecting to be able to have data to analyze on schedule.
Okay, I think that kind of works.
That data will help us understand. That data will help us understand things such as, for example, they're looking at the last time that photons bounced off of essentially gravitational waves that were in the early universe.
Now you're talking about the period of time where the universe was kind of opaque, and that there's just like a sea of electrons, light couldn't really escape.
Yes.
And then the recombination period happened. Electrons combined with protons to form neutral atoms, and then all that photonic energy that was there was allowed to burst out in a cosmic flash.
Yes.
And that's what we see now as the cosmic microwave background radiation, correct?
Yeah, and yes, and those that last ricochet before the universe went transparent imparted a particular polarization on that material, and so they're looking at that polarization, and there's properties that if we have these ways, for example, that LIGOS was able to detect, that were dominant in the universe, that were part of the result of the inflation period, then they should have these certain properties. So they're trying to detect the last ricochet before the universe went transparent, and pin down perhaps when the inflation period might have started and stopped.
Okay, next slide, and then we're going to dive into each of these. Well, hopefully they always get good data. All right, so I call it the cosmic event horizon problem. You call it the horizon homogeny problem, or homogeny or homogeneity. How do you prefer it? I call it homogeny, but homogeneity. Okay. So horizon homogeneity problem. Basically, how could regions of space that are too far away due to the speed of light remain homogeneous effectively at the same conditions without some kind of mechanism that sets the same initial conditions everywhere? So when we look at the background radiation, why is it so similar with a very small temperature differential? Why are the constants the same? Why is the fine structure constant similar in all points in the universe? And I'm going to kind of let Dr. Kroon kind of jump in on this one. Why is it that we see a lot of homogeny in the universe, but we still see many things like answer entropies, which are irregularities in the cosmic microwave background radiation as well. And is that somehow set from whatever the initial conditions were of the Big Bang? Is that what we're seeing now the result of those things?
Yeah, kind of. Well, yes. But one thing that I did read about is how they were trying to look at variations in the speed of light arbitrarily far back in time to look for variations in any of the fundamental constants of the universe that dictate the speed of light, and other things such as the wavelength of hydrogen Balmer emission lines. And they found that essentially the speed of light has not changed. So it seems like the laws of physics and the constants of the universe were constant to a very high degree throughout the age of the universe.
So there's a natural relationship between all these natural units, right? So when you have like gravitational constant, you have like the speed of light, you have Planck's constant, you have the fine structure constant. There's a relationship between all of these, is there not? Such that if any one of them changed, all the other ones would change somehow, including the speed of light, because the speed of light is very dependent upon things like the fine structure constant, and as well as electric and magnetic permittivity and permissivity, right? So if we did have the speed of light change in the initial conditions, could it be feasible to even say that our universe would not be the way we know it now?
Yeah.
So a good thing that it hasn't.
The speed of light, which is dependent on the permittivity and the permeability of free space, would show up again in things like the fine structure constant, which dictates things about like the strength of chemistry, how chemistry happens. That would affect biology and molecular forces that bind comets and planets together under the action of gravity. There would definitely be a very different universe if you changed any of these by a lot or even a little.
Okay, so the inflation model was put out there to try to resolve this particular homogeneity. I hate this word.
Homogeneity.
I call it homogeneity.
I say it I say it the way you do. Homogeneity. I say it, but he says it otherwise. So I guess it's like potato. But it is homogeneous. So
I've heard when people say homogeneous that's wrong. That it's homogeneity.
Really? See, I don't. I guess
homogeneous. Like what part of?
Yeah.
You know
part
what?
of my dissertation and
go ahead.
Part of my dissertation had inhomogeneous and homogeneous.
Okay, so your dissertation you use homogeneous.
Homogeneity. Yes.
Exactly.
Wait, we gotta get this right. So Athena's going to be the tiebreaker. So hang on, Dr. Kroon, you say what?
For this particular word, homogeneity, and homogeneous for it's the other version of that.
Okay, and Landon, do you agree?
Yes.
Homogeneity. Okay, Athena.
Yep, homogeneity.
We're gonna go with homogeneity then. Okay, sounds good. Right. This is how myopic we get on this program. We have to make sure that we pronounce homogeneity correctly. All right, next slide. She's never coming back, people. Okay, next slide. She's like, what am I getting myself into?
I'll make a whole video about homogeneity.
Exactly. We might have started a whole new series, the homogeneity series. Okay, so the homogeneity problem. The solutions were the cosmic inflation model, which we had talked about, and I think you mentioned obviously the variable speed of light model, you kind of touched on that they were kind of playing around with if the speed of light can change, that would kind of solve this issue, right? And the reason why we pick one over the other is because there's really no evidence that the speed of light has changed. Would that be a fair summation?
Yeah.
Okay. Yes, I mean,
by the way,
like he's mentioned, like the fine structure constant, other things, it would be relative as would be observing a radically different universe if the speed of light were variable. And so the two possible solutions, cosmic inflation and VSL, considered, but observational evidence favors inflation model and not variable speed of light.
You're breaking up a little bit, Landon, but yeah, we got most of that. We got most of it.
Sorry,
the younger creations out there.
Yes.
Just hang on. The younger creation out there, there's a couple of them watching. Pay attention to this because this shit's all over younger creationism right now. So just bear in mind that when they talk about things like accelerated decay, they talk about things like asynchronous light. Yeah, not going to happen. So because we exist, and
there is
zero. We would not exist.
There's zero evidence that the speed of light in a vacuum changes.
And that's good that you mentioned that because we are talking about C, which is speed of light in a vacuum. Speed of light is a constant in a vacuum. Can light be slowed in various mediums? Yes, of course. But that's not what they mean by changing the speed of light. All right, next slide. The monopole problem. A large number of very massive, stable magnetic monopoles, theoretical particles with a net magnetic charge, basically a magnet with one end, could have been produced early in the universe due to spontaneous symmetry breaking from a single gauge theory. Why have no stable monopoles ever been observed? Now, I'm going to turn this one to Landon because Landon kind of rewrote this. I had my version of it, but he wrote it. Why do we have to care about the monopole problem, and what actually is it in relationship to the Big Bang?
Well, there's a thing called gauge theory that would state that we should have these particles, theoretical particles, with a net magnetic charge that should have been created, and the assumption is that these particles, should be out there. So people went and looked for monopoles, and the problem was that we're not finding them. Now, are we not finding them because we don't know how to look? Or we're not finding them because they don't exist, or we're not finding them because they're rare. Well, the way that the universe began, there should have been massive stable monopoles according to the models that we use, and we don't see them. So what happened?
Now, that doesn't mean they don't exist. Like, correct me if I'm wrong. We've discovered monopoles. We've discovered decay things in monopoles, but they're induced. Either they've been produced somehow. They're not primordial monopoles that we're talking about because those would have long since decayed. But we have discovered monopoles exist, right? Anybody?
Not to my knowledge. That would be
not to my knowledge. I don't know.
Because I've read things up. They found decays that they would expect from a monopole. So I have read things out there that if it discovered that these monopoles do exist, but they're not primordial. Well, I could obviously be completely wrong on that, but we'll have to look into that. But from what I remember reading, they did find decays that they would expect from monopoles. What they would, if they did it, they did exist.
Could you maybe have been thinking about condensed matter physics monopoles, which is a different?
Yes.
Well, I mean, possible. I mean, I look at condensed matter. Condensed energy is matter, and then condensed matter would be like Einstein's Bose constant, right?
Yeah.
Very, very cool cryogenetic stuff. Helium frozen down to absolute zero, that kind of stuff.
Yeah.
I think that might be it. I mean, because they have things that are basically what we would look for, what a monopole would look for in those kind of condensates.
Well, but again, I'm looking over literature again, and I don't see that there has been ever a confirmed detection of a monopole.
Okay.
I'm looking around. I'm not seeing anything. I was just checking to be sure. Now there are quote monopoles in condensed matter systems, but that's a different thing. That's not talking about a fundamental particle.
Okay, that could be what I'm referring to. All right, next.
There are certainly people that talk about macroscopic black holes are potential magnetic monopoles, but that's a Einstein-Rosen bridge stuff. So
okay, so the monopole problem continued. The pre-inflation monopoles, they would not be stable if they existed, right? So they would have decayed. We wouldn't detect them if they don't exist. They became separated from each other very early on because of inflation, and then have a very, very low density, which I would imply there's not very many of them. And then that it's more likely that they're not stable because we've been looking for them and we haven't found any, according to what Landon's saying. Is that correct?
yes. So think about it this way: that gauge theory should have suggests that we should have created monopoles, but if one of the things you get with inflation is that between the Big Bang and the start of inflation, you would have either had monopole decay, or if monopoles weren't stable, but if the ones that survived would be at a very low density today, that they were created pre-inflation, and inflation separated them out. So now they're so sparse that we're having difficulty finding them.
Yeah.
Gotcha. All right, next slide. The flatness problem.
Oh, yeah.
Small deviations in density of matter and energy, omega naught, would create extreme effects in the universe we know today. Why does the universe appear to have a flatness of 1 to within 1 part of 10 to the 62? Now, the way I remember this, the local geometry we've discovered is flat. It's up to like 6 sigma or something. You say it's higher, but why does the Big Bang, or why does the inflation theory in Big Bang kind of resolve this flatness problem? Landon?
I mean, one of the things that happened is with the according to the model is that the universe was able to during this inflation period was able to start off with a very okay. Actually, let's back up. What do we mean by flat? That's at first, I guess, one of the first things you have to define. Let's first of all define our terms. When we say the universe is flat, what I guess a layperson's way of saying is that right angles are at 90 degrees, parallel lines don't meet. That for example, a non-flat universe would be where the universe curves in on itself, right? That it looks more like a surface of a four-dimensional sphere, as opposed to being flat everywhere. So when you put a large triangle into the universe, do all the 3 points do the angles of the 3 points sum up to 180 degrees? You might say, well, of course, because that's what triangles are. Well, if space is curving, then you could have your vertices of the triangles come out much narrower and splay out. So you could have, for example, if you take a surface of a ball and put 3 points on that ball, and draw the great circles between those 3 points and measure the angles, you won't see 180-degree triangle.
Now space is non-Euclidean,
though.
I mean, it is curved, though, right?
Yes, but the question is how curved is the overall cosmos? Is the grid of space relatively uniform? I'm not talking about local distortions in it. I'm talking about the overall big geometry of the universe. Is it flat?
Yeah, well, growing up, like when I were to be like Paul Davies, it was said that if you took a telescope and had an infinite amount of power, you could see the back of your head. Does that no longer apply?
I would say.
Go ahead.
I would say no, because the observe. Well, so we have our own. Essentially, like any whenever you look off in any direction, like we're at the center of our own observable bubble of the universe. So like you wouldn't just require infinite power, you would require infinite time and a bunch of other crazy stuff for light to be able to curve,
Sure,
not
of
just
course.
around the space part, but also the time part. And so I never heard that before. It's an interesting thing to ponder, though.
Yeah, if you were to look through a telescope, I'm trying to just imagine it, you would have to outpace the rate of expansion of the universe in order to try and not even just go faster than the rate that we're expanding, but to be able to then see yourself again. That would
this makes certain
that
assumptions.
really is interesting.
It obviously doesn't take into account acceleration, cosmic expansion. I mean, this is a very simple thing that they used to say, giving, just based upon power, not taking into account the time element. But that's only trying to relate the curvature factor, right? So we know now.
Steve, you're correct.
The universe is pretty well.
It's the accelerating universe that says no, you're not going to see the back of your head, even if the geometry would otherwise allow it. I mean, think about when we talk about an object being 5 billion light years away. What do we mean? What we mean is that at the time when light left that object, right, that we seeing an object 5 billion light years, the universe was of a size such that it took light 5 billion years to reach us. Our now is includes their then back 5 billion years ago. But if you talk about, if you want to send a signal back to that same object that was where we saw light traveling to us for 5 billion years, it's not going to take 5 billion years to reflect that light back. It's going to take more than 5 billion years because the universe is expanding. Now, that's not inflation. Inflation's a different thing, but that's expansion of a universe.
Due to dark energy, they hypothesize. Okay.
There is this thing. There's this thing we have to talk about in terms of density of matter, matter and energy in the universe, where if again it's that omega naught value. If it's 1, then the universe will be essentially flat. Or, for example, if you had a curvature that was greater than 1, then the surface of space would be more would wrap around on itself, would be enclosed. You might think of it like a sphere. What do you mean with sphere? Well, if you take the dimensions, our 3 dimensions, and map them onto a 4-dimensional sphere, does it reach around and as you say, meet itself? Ignoring the fact that you couldn't see the back of your head, would the geometry cause the lines to wrap around the universe and come back to you? Like going around on the surface of a sphere gives you a 2-dimensional analog of this wrapping around. There is omega less than 0.
Now because of the expansion, right? Because we didn't know the universe was accelerating when I was a kid, by the way. That's actually, I think, 90s or something. So that's relatively new.
Yeah, 98.
Yeah. Okay. So I mean, I wasn't a kid in '98 any longer, unfortunately. But yeah, back in when I was in high school, that's the way they kind of related it. But anyways, next slide. This is I'm going to turn this one completely over to you guys because I know nothing about topology. So you guys can have at this because these are some of the potential solutions. I don't want to get into too much detail on this because I think it kind of goes away from the whole Big Bang thing. But do you want to touch on this real quick since you wrote this, Landon, and then maybe Dr. Kroon can weigh in on it a little bit, and then Athena?
Oh, okay. So one of the solutions is to say that essentially the inflation stretched out space-time to be flat, right? That you might have had a different geometry in the pre-inflation universe, but the rapid doubling in sizes over a very, very short period of time of space stretch things out to become flat, or at least close to as flat as we can observe today. There is a different theory, Einstein, that is possible to be invoked, which is sort of Einstein Cartan theory, that talks about essentially that the theory it removes the constraint of symmetry of what's called the torsion. Basically, that torsion tensor becomes a dynamic as a dynamic variable. So you can get interesting stuff about the fact that it gives correct data for conservation laws for the total angular minimum, let's say, of matter in presence of gravity, but it's assuming something called that you have these sort of things called Dirac spinors that are obeying these nonlinear Dirac equations. They're trying to come up with a way that is an alternate to how the universe could become flat. Einstein-Cartesian theory would assume that the universe will have rapid expansion followed by a contraction and a balance. And that's something that's troubling that particular theory, because it appears now that we're in an inflation-only period. But what to say is that there are two possible solutions. One is during inflation, space got stretched out to where again, right angles are 90 degrees. The geometry is regular in the type of grids you typically see in graph paper, or that there's a alternate theory that revolving around torsion tensors and nonlinear Dirac equations that could also explain it without inflation. However,
all right,
if inflation is fixing, it seems to be favored in fixing the monopole problem, and it seems to be favored in terms of homogeneity problem. One might also see that inflation could also fix the correctness problem. That's one of the reasons why Einstein-Cartesian has not been ruled out, but it certainly is not favored because inflation is fixing the other two Big Bang problems so well.
Dr. Kroon, do you want to kind of add anything to that? Because probably most of this will go over most people's head. I think the main point is the anthropic principle, but which I can explain, obviously, that if it weren't one, we wouldn't be here. The anthropic principle is that the universe is such that we are here to observe it. If we are creatures that are allowed to observe the universe in a way such that we exist. I mean, if we didn't exist, we couldn't observe the universe. So, but how would you kind of resolve this flatness problem using the Einstein-Cartan theory in a nutshell? I don't want to get too deep in it.
Well, yeah, and in lieu of not repeating the very elegant way that Landon described it and all the stuff we have on the slide, I would just add something that I've always found to be kind of interesting, or at least noteworthy, which is that if you consider, if you think about the Big Bang from the lens of sort of like the quantum foam and the uncertainty principle, and you think about how the universe, just like anything else in the universe right now, can sort of pop into existence from nothing, borrow energy from nothingness, so long as it pops out of existence in less than that delta t, where delta t is less than or equal to, or greater than or equal to h bar, over delta E, whatever that uncertainty is, the uncertainty principle with the canonical variables energy and time. And so what's kind of neat is if you realize that once, let's call it a candidate universe, has popped into existence and at a quantum scale, and it's still more or less a singularity. If there were a force that inflated it so fast that it became macroscopic before that delta t sort of expired and it was sort of required to pop out of existence, then it could sort of, quote, like grab hold of reality and become a real quantum universe that is nascent and ever expanding and becoming even more macroscopic, if you will. So
basically, it's a violation of uncertainty principle, though. I mean, the Heisenberg uncertainty principle would be a relationship between position of a particle and its momentum, right? And you're saying there's an uncertainty principle with relationship to energy and time, and that a violation of that would cause the
I would say a back door. Let's say just same thing with like Hawking radiation. Like those particles are supposed to pop back out of existence, but something else that was unrelated to the principles that governed the initial appearance of these entities from nothingness caused it to go at a right angle to that originating principle, that original paradigm. And so the inflation is definitely something that, even though there's all these ways to discuss it and study it, I would almost consider a placeholder word for something that we know happened or happens, sort of like a different phenomenon, like a dark energy, which is likely unrelated completely to it, but like I said, sort of a placeholder word for phenomenon that we infer out of necessity to have happened, and can study some of its consequences, even in an indirect sense in the universe today, making it much more legitimate than a simple hypothetical hypothesis, if you will, more of a model that works for what we see right now. And if you got something better, let us know, sort of a thing,
No, that makes a lot of sense. I mean, it makes sense that there's maybe a mechanism allows for that. I mean, I think the analogy makes sense to me, that people may not know, but like Hawking radiation is, if you have a boundary condition on the black hole and you have a virtual photon pair produced, there is a situation, depending on what orientation that they have to the boundary, that one photon can actually go into the black hole and the other one gets imparted to become real. They're not just virtual photons. There are real particles that come out of that. And then you have a boiling away of a black hole. That's why small black holes are going to boil away really fast, but larger black holes not so much. But we can actually detect this radiation. We know that it exists, and we know the mechanism behind it now. So you're saying that you think there might be a mechanism.
It's a curvature issue, right? The small black holes have high.
That's to do with the surface area of the black hole, right?
Yeah.
Okay.
This actually ties in really well with the no boundary proposal. Just to jump in really quick, what Dr. Kroon said, and that's awesome. And I know we're leading into that in a couple slides, but that's just really, really interesting to think about, because also what Landon was saying, and I never thought of it this way before. He said that we're kind of in a stage right now that is sort of like an inflation period, because we are expanding. So right now, does it mean that this ties into then that we may potentially end up resulting in a big crunch, where if we actually formed out of existence, then we can fall out of existence just as quickly? And this also, again, would tie right into what Dr. Kroon was saying about the no boundary proposal, which was taking quantum mechanics, and he applied it, Stephen Hawking applied it directly to black holes, and started measuring, as you said, like can actually measure Hawking radiation, that when a particle enters the black hole, part of it's radiated back out into the universe, where exactly it will boil out of existence. And so if this is possible, where you can take the mathematics of quantum mechanics and apply that into the macro scale and the cosmos, then does that mean that those two can actually go hand in hand? Because the homogeneity problem, well, not problem, but the observation of the universe being homogeneous, and seeing that physics applies to all the universe, physics changes when it comes to the quantum scale. So if you use the physics from the quantum scale and the way that quantum particles work, and apply that to massive, into atoms, and then the mass scale of the universe, then does that mean that what we may observe happening to particles on the quantum scale actually be happening in the macro scale, meaning multiverse, meaning a superposition of particles? Does it mean that we're existing here and also somewhere else? But that'll tie into quantum physics we can get into another time. But I just thought that was interesting that he was bringing that up about the different principles from the no boundary proposal principle itself. So I just wanted to chime in about that a little bit.
Yeah, no, that's a brilliant lead. That's why people on the outside, this is why we're talking about each one of these topics. She just literally just did my presentation in a nutshell. It's brilliant, because these are why these are. No, it's great, because people might be going, well, what does this have to do with the topic? There is a correlation here. There's a reason why I picked these particular things to talk about, to try to discuss this topic, and I think that you did a brilliant way of pulling that all together. So,
there's several things also to understand. when you're talking about cosmic inflation, we're talking about, the typical model says that an epoch that began, lasted somewhere around 10 to the minus 36 seconds, a really tiny bit of time, and that the Big Bang Solaris that the notion that in the inflation where the universe began to rapidly expand, that rapid expansion, the extreme rate of expansion slowed down, and today continues at a less expansion rate. So one of the things that most models say, inflation kicked off shortly after the Big Bang, and had a rapid period of time, and that slowed way down for some reason today, where we have a less rapid rate. It used to be that we said inflation turned off, and because we didn't know that our universe was still expanding or accelerating. But now with observational data, we know better. I want to be back to why do we bring up this Einstein-Cartian theory? One of the things that the Einstein-Cartian theory does is it averts the need for a Big Bang singularity. Instead, it replaces it with a bounce that the universe had sort of a minimum scale factor, perhaps at the Planck level, and that what Einstein-Cartian theory might favor is a universe that is cyclic, where it expands, stops, contracts, and bounces off itself. And so the Big Bang was the last bounce, where it didn't reach singularity, it didn't reach an infinite density. There was a minimum scale that the universe bounced off of.
And I'm glad you brought that up, because we that kind of goes into the whole time element that we're going to be getting into, the big bounce over the Big Bang. But the Big Bang is just part of the big bounce, right? I mean, the Big Bang is not exclusionary.
Remember
big bounce, right?
That the rapid expansion immediately after the bounce explains why the present universe appears to be spatially flat, homogeneous, and isotropic, right? But the question is, did it come from a singularity, or did it come from a minimum scale?
Gotcha.
And that would so this is an alternate way to explain what? The flatness, right? This doesn't say that Einstein-Cartian theory disagrees with inflation. It may be that inflation is that if the Einstein-Cartian, I think it's Shima-Kibble theory of gravity is reasonable, and that we have a minimum scale, that they don't have singularities, then you can from that you can get a flat universe without the need for a singularity at the beginning. Inflation can still happen. It doesn't mean that inflation didn't happen. It just means there's an alternate way that you could get a flat universe, or apparently flat universe.
We got to pick up the pace a little bit here. We're over an hour right now.
Sorry,
Athena, do you want to? That's okay. I know you can go on forever. Did you want to add anything? We go to the next slide, Athena.
I'm good.
Okay, next slide. She's like, I'm not following that. I wouldn't either. I mean, Landon could pretty. I've seen him do it actually. 8 hours long, just talking about science, specific topic. I mean, he can do it. Okay, so why is this an important question to the initial question? Why is it important to the initial question? Do you understand why Big Bang theory and inflation theory makes the initial question nonsensical? We're going to dive into a little math here. Now, I want to warn you people, this is going to get a little mathematical. So if you have any math phobes out there, you can take them out of the room now. We don't mind. Go get some caffeine or something, because we don't want your brains to implode, okay? Because you have to deal with math sometimes. It's just a reality of dealing with these topics. So we're going to just kind of dive right into it, and then we'll let these experts here kind of explain the details. But let's go to the next slide. Yeah, well, you do, right? I mean, you got to have some math and physics, right? Is this
math phobes? That's a good term.
Math phobes. Yeah. We have a lot of math phobes. So the Hartle-Hawking state basically is the conditions for the no boundary proposal that we're going to be talking about. Basically, what he hypothesized what would happen if we can eventually rewind the universe to t equals 0. Now, that's just given the assumption that, time is some kind of ongoing thing. We have an arrow of time, which is based upon entropy. The arrow of time is considered to be the difference between entropic states from lower to higher, because we all know that the universe is increasing in entropy. And they basically hypothesized what would happen if we just kind of rewound the universe. And as Landon pointed out, does it get to a mathematical singularity, or kind of get to a boundary condition where we don't have that singularity occur? Because we all know by now, general relativity breaks down at time equals 0, right? General relativity can't really model what happens at that singularity. Now, you can evolve things like called loop quantum gravity to help do that, which the no boundary proposal, as far as I understand, kind of does. But loop quantum gravity and general relativity don't play well with each other. They don't like each other. So they're kind of incompatible as it stands now. Would you agree that's a kind of a fair summation?
Yes, I want to point out what do you mean by not compatible is that you'd have to go from, if you said loop quantum gravity is reasons, you have to say, well, how do you go from loop quantum gravity to general relativity? Right, because we see general relativity is measured, has been measured and well confirmed multiple times, directly and indirectly. So how would you go from a loop quantum gravity did it to we have general relativity today? That's probably the bigger hurdle you'd have to overcome.
Everybody else agree?
Yeah.
Okay.
Oh yeah.
And so this is kind of describing the conditions to the Planck error, prior to the Planck error. Planck error ended 10 to the negative 43 seconds, I think, wasn't it? We're going to go with that.
Yes, that's usually a Planck time unit. Yes.
Okay.
Yes.
Next slide. Okay, so I wrote this, and I'm going to run it by you guys. This is how I kind of look at it, and you just have to tell me if this makes sense to you all. The way I look at it, for quantum loop gravity versus general relativity thinks space-time is more of a four-dimensional, what's called Minkowski space. Basically, space-time is integrated. It's a manifold, so to speak. Where you have, opposed to a neo-Lorentzian model, where you have three spatial dimensions with one time dimension. In each case, space-time is malleable. We know that it can basically have deformation because that's all gravity is, mass, deforms space-time. We also think they can actually rip, what's called the big rip. But there's not a preferred frame of reference in general relativity. Means that wherever you are, that's your preferred, that's your frame of reference, but there's no preferred frame of reference to the entire universe. So there's no such thing as absolute time. One of the things that they talk about is relativity of simultaneity. So if you have two events that are spatially separated and they occur at the same time relative to a frame of reference to the observer, but they're not absolute, such that from different frames of references, they would actually see one event happen prior to the other one. How do you guys think that kind of relates to the well, what I just made makes sense, first of all?
Oh yeah.
Yeah, it does make
So I'm
sense.
not way off
enough
field. Athena, go ahead.
Yeah, yeah. Well, it definitely, makes sense just coming from like a more of a basic observational standpoint, as opposed to diving in deep with anything. Because I know we're about to do that. But just
I'm a
looking at things like
I'm simple. I'm a simple
yeah.
man.
And I who usually I work with kids a lot of times at museums, so that's kind of how I break down my science. But yeah, so when you think about that, exactly what you just said obviously makes sense, because you think about it and you think about like when you look at things from two different perspectives or whatever it is in the universe, one thing might be observed at a different time than another. Perfect example is the International Space Station is traveling a bit faster than we are, so they're actually aging a little bit slower than we are. So they see Earth traveling at a certain rate, but then we see it traveling at a certain rate. And if you expand that into a much broader scheme of things in the universe, something much, much further away, like a rocket ship, and this is just talking about like time dilation, and you take two atomic clocks and you synchronize them, and then you put one on the rocket ship and one here on Earth, it's going to see our clock ticking much slower, and eventually might stop ticking because it's moving maybe at the speed of light. It's moving much faster than we are. And its clock is going to still be ticking at normal rate. So it can do a full loop around something, let's say sort of like a black hole, for instance. It can, if it for some reason can loop around a black hole and not get pulled in by its gravity, it may be traveling at about twice the speed that we would be traveling here on Earth, which means that people there would be aging at about half the rate that we'd be aging here on Earth. So what you kind of just said, and that's tying into a little bit different. That's more about special relativity, but yeah, it's something that it has been calculated. It's been observed. We've actually done experiments about this. So that's
these are confirmed things. Yeah, the relativity is confirmed. No matter what anybody tells you, it works. I'm a scientific instrumentalist, not a realist. I think maybe we might have some scientific. I think what they call them. What do you call yourself, Dr. Kroon? You're not an instrumentalist, or what are you? A scientific what?
I don't know.
John.
We didn't. You had to.
Yeah.
You had to.
We have to finish the discussion.
That conversation.
Yeah, we didn't finish it. But what'd you call yourself? You had a term I hadn't heard before. A scientific coordinates.
Hold on. I can go back to
he made up a term, and I liked it.
It made sense at the time, like in my defense.
Yeah, no, I liked it. It was a good coinage, actually. I didn't know what he was talking about. I've never heard this before. He's like, I just kind of made it up. But I was like, it works.
I want to know what it is. What is it?
Yeah, I don't know what it is, but it sounds really good.
Okay, so while he's looking it up, one of the things that you're talking about in terms of measuring, she was talking about time dilation, right, and time slowing down. One of the things that's going to happen, there's a space probe called the Parker Space Probe that people focus on. It's going to get really close to the sun, do these flybys to the sun to observe conditions now near the surface of the sun. But one of the other experiments it's going to be doing is another test of general relativity. I don't know if you know about this, but when the Parker Space Probe is at its maximum speed, where it's closest to the sun and zipping around and in its spot, it will be traveling close to 700,000 kilometers per hour. So that's about 430,000 miles per hour. That's a very non-trivial speed. And we are going, it has, the space probe has clocks on it for synchronizing events and sending out signals. And we're going to watch from our standpoint, this clock zip around near the sun. It's going into a more intense gravitational field, and we'll see time literally slow down for it, right? It will, time will run on that spacecraft at a slower pace than what we see here on Earth, and we'll actually measure that to a very fine degree. Yes, with respect to us.
We have to know with respect to us. If you were on that time, if you're on the probe, you wouldn't notice a difference.
Spacecraft,
we'd be actually running fast.
Everything.
Yeah.
Yes, and so you look back on the universe. But anyway, that's something that's going to be tested very well.
And
by the way,
I
found out what
was it called?
Yeah.
What did you call it?
So I'll read you the little blurb I had. I said, am I a realist, a pragmatist, a scientific rationalist? There's probably a term for me. I think that third one is it. Does that sound familiar to you, Steve?
No, I think you said you were because I asked like a scientific compatibilist or something. Because I asked if you were instrumentalist or a realist, because a scientific realist would take a scientific theory and say this is actually the way the universe is, and a scientific instrumentalist just says, you know what, it doesn't matter whether it is or isn't. We can use it to model.
Oh, here we go. So I scrolled down more. You said that you're an instrumentalist, and I said, I'm kind of both. I'm what I might call a circumstantial instrumentalist.
Circumstantial, yeah, that was good. Yeah.
And I could think of scenarios that unambiguously conform to either paradigm, and then I said I'm a mutant. Yeah. LOL.
But
yeah, that was actually
good. Never assume that the universe gives a damn about your theory. That's one of the things my advisor kept hammering in on saying.
That's why I can't. I can't adhere to scientific realism.
It's very important here. The universe does not ask your permission to do what it does. So your theory does not tell the universe what to do. Your theory is you make a theory in order to try to predict what the universe is doing, and we accept or reject your theory based upon evidence, based upon observation, right? That's so your theory has to be observable, which
doesn't prescribe the way the universe must be.
Yeah. Which is just why the string model does not deserve the word theory. at this point.
Yeah.
Because
Well,
it's not
I
really
don't,
that
I don't
testable.
know. I mean, I'm just kind of still reading the cosmic landscape, but you know, as a mathematical, they call them theories in mathematics because the mathematics works for string theories, from as I understand.
Well,
So that's
mathematics would be a
the way.
model.
But we're
No,
gonna dive into string theory.
What's this?
We're
What's
gonna
this
be here another
math
5
theory?
hours.
What is this math theory thing? Okay.
What is this math we're talking about? But real quick, I was gonna say something else. Oh yeah, Athena, it's funny you mentioned time dilation, and all that, because this episode was originally going to be just me and Dr. Kroon, I think, and probably Landon, but I don't know if he was going to be available this week. But it was either this weekend or last weekend. Last weekend, I think it was. We were going to talk about time dilation and how muons show us that time dilation works, but we'll say that for another time. But next slide. But it's so funny you mentioned that because we were going to do a topic on
What are
that.
the chances? Yeah, that's funny. Cool.
All right, key points of general relativity. General relativity, the way I describe it, is it basically models the shortest geodesic path between two objects. So it's kind of like a straight line for curved space. General relativity holds time as emergent from three-dimensional space-time curvature. This is due to energy distribution. So general relativity really kind of thinks that time is an emergent property of space, and that's kind of a critical thing. And that general relativity maintains a classical trajectory between 2 points. So if we wanted to get from A to B, we have to go through what we would call normal space-time, and that is the shortest distance for us. Even though if you could actually like do a wormhole or something like that, you could theoretically make a shorter distance. Just like if I could tunnel my way through the Earth, I can get to the equator faster that way that I could going around the circumference, right? So that's kind of the key points for general relativity. Simple, but want to add anything to that, anybody? Or is it pretty basic?
Hit the nail on the head
there's
there.
always that that thrifty saying that goes, matter tells space-time how to curve and space-time tells matter how to move. That's always we can't have a discussion of GR without that little thrifty turn of phrase.
Very
and
nice.
as you can tell by the diagram,
nice,
the sun is the body of mass, and it tells space-time how to curve. You literally are following the curvature of left of that potential energy well of the sun. Now, this is only a two-dimensional cross-section. Remember, people, this
By
is
the way, that diagram is not curved to scale.
No,
Right.
It's not curved to scale. Thank you, Landon. People were kind of concerned about it, I'm sure. All right, next point. This is where we start getting into the fun stuff. So this is some of the key points of quantum quantum gravity. So what it usually is called the path integral formalization, and I'm going to have one of you people talk about it here in a second. But the PIF is basically a way to calculate every possible trajectory between 2 points and find the likely path between A and B for which a trajectory was taken. Now, the path integral formalization is literally based upon wave functions, and that a particle will take all these different paths, but as you measure something, then it actually manifests only one path. But it's actually existing in all these different paths simultaneously, which is something weird in quantum, being in multiple places at the same instant. But this, what it actually does is it looks at every single infinite amount of paths you can take from A to B, and basically has a formula that says all these paths are taking at the same time. That's the way I'm kind of looking at the path integral formalization. I know all three of you have talked about this before, so who wants to kind of jump in on this first?
Landon,
you'll take forever.
Start?
So, Landon, go ahead. I'm just kidding.
Well, I mean, I know that Feynman did a lot of stuff with path integral formulation, and I remember him saying that yes, because I was as a kid saying that seems kind of absurd. It said yes, one of the possible paths is a particle starts off, goes the opposite direction, goes down to the corner drugstore, goes around the clerk 3 times, and comes back. That's a possible path, and that's one of the he was trying to illustrate saying that's one of the infinite paths that a particle can go from going from A to B. But it said that they can do the calculations because most of those more so-called ridiculous paths tend to cancel out, and what remains is the shortest possible trajectory between 2 points.
Now these are possible.
Except when you get in.
I mean, there are paths that are just not possible, or as you said, most of them will cancel out in some way, right? Because they're based upon wave
Yes, when you're
functions.
trying to calculate everything, the functions around all these absurd paths.
Yeah, it's like a quantum mechanical analog to the principle of least action. I mean, the integrals do
exactly.
involve the Hamiltonian operator, and you pick up a phase, which will sort of describe your final amplitude for these ridiculous paths, and you get a lot of cancellation from the math. You get these handy dandy e to the minus
Now, one of these
I,
days, oh, sorry. Go
and
ahead.
then e to the positive I to the such and such, and there's a lot of cancellation there, and you get it's a lot. There's a lot. I could talk forever about that stuff.
It's a wonderful subject, and one of these days I do want to get somebody that I know. Her name's Jade. She did a wonderful presentation on this particular thing, and I wouldn't mind getting into some of the more complicated things because I have a very, very basic understanding. Like all I know about a Hamiltonian operator, and you're probably gonna laugh at me, but as far as I understand it, the only thing it is basically like the Hamiltonian of a psi function is equal to the basically different states of the energy of the psi function. So basically, they're eigenvalues and eigenstates of possibilities. That's the only way I can possibly relate a Hamiltonian operator because I've never really worked with them.
Yeah,
but they are related somehow to the different ways you can have energy relating to your psi function, something along those lines, eigenvalues and adding vectors together for transformations.
Yeah,
I'm explaining it really poorly. Maybe you can kind of clean that up.
Me or Landon?
You.
Yeah, so you could think of the Hamiltonian as like a propagator. It's T plus V, your kinetic energy plus your potential energy, and then remember the Lagrangian is the kinetic energy minus the potential. But here we have T plus V, and so you could write down these quantum mechanical operators that essentially depend on Q, which is your coordinate, like X, Y, Z, your position, which is related to potential energy of the system. And you could write down the first time derivative of the coordinates Q, which give you your momentum. So you have P and Q, which are these sort of non-commuting operators. And so you might remember those two guys from the uncertainty principle, delta P, delta X. So they like to pair up. And so you have them both showing up in the Hamiltonian operator. And you essentially add up all the possible paths, and they're weighted by the phase which pops out front, and you do these integrals, and you get so essentially the Fourier transform. So it's interpreted as a matrix multiplication. The sum over all states integrates over all the Q's and takes the Fourier transform in Q to change basis to P. And so the action is on the Hilbert space. You're talking about the Hamiltonian propagator and phases that that ultimately determine the amplitude. And so you get a lot of cancellation, and you get the more probable paths. You can still have multiple paths that the particle could take, but you may not have all the ridiculous ones happening regularly. You'll still have a bunch of them that are possible to go from A to B, but it doesn't necessarily all cancel out to just one path. So you add them all up, and it's all normal.
We could probably make a whole presentation on each of those, right? I mean, we can go into Fourier transformation. The only thing I remember, I did work with Fourier, but that was basically going from a frequency domain to a time domain. Lagrange, I remember kinetic energy minus potential energy. Is that right? Yeah, no, I think that each one of them could probably spend about a whole 2 hours just talking about different way to do transformations, but they're all based upon matrix theory of some way. They're all talking about different vector spaces and Hilbert spaces, as you mentioned. But the path integral formalization, so this right here is a lot different than the way quantum GR looks at it, right? GR looks at a single shortest geodesic path, but the loop quantum gravity looks at an infinite number of paths, basically, right? And then takes a summation and then finds the best possible path. Okay, next. So the way I would describe a wave function, and again, I'm going to turn over to you guys, but a wave to function is something that describes a system. You have the psi, which is your wave function, and your psi squared, which is the probability density. And the way that I kind of relate them is that if you have a wave function, that's going to give you, let's say you have a standing sinusoidal wave, like shown in the little diagram there. Let's say the first, we'll call that the first fundamental, and the second would be the next. So in this particular first fundamental, you would have a wave, a sinusoidal wave, right? That's the top half of a sinusoidal wave. And the probability density is basically the likelihood of finding a particle at a given position given that sinusoidal wave. So at the maximum amplitude of that wave, that is the area where I would most likely expect to find like an electron in an orbital. Think of it as a range that electrons could exist with respect to the nucleus. So they're in this bounded condition. We call them the s orbital or the p orbital or the d orbital. But they're bounded in such that you're not going to find an electron in a transition zone. You're going to find a very low probability of finding an electron near the point where the sinusoidal wave starts to meet the x-axis. But as the sinusoidal wave reaches this maximum, that's to be the most likely place you're going to find an electron. And in quantum mechanics, the electron is everywhere. It's existing the entire spectrum of that boundary, and it's not even at a specific point until this is actually observed, which is another thing that's quite distinct from what we see in macro scale. So the second one would be that sinusoidal wave. Each one of those is basically, the top part would be, again, where the particles more likely to be found. The null would be where it hits the x-axis. So this is a relationship between the probability wave density and the wave function. Now, maybe you can kind of like expand upon that a little bit. Matter of fact, Athena, you want to take this one? You dealt with this one a little bit.
Yeah, I'll jump into this one. So branching off of actually what we spoke about just before this, it ties in well with this because, as you said, that there's two different behaviors happening when it comes to the macro scale and then the quantum scale. And so this is extremely important because we notice when observing quantum particles and the way that they behave, there is something known as a double slit experiment, where this, I'm just going to relate this for a moment, this is actually about a pathway, two different pathways, and shooting specific quantum particles through it. And they noticed that there was a whole scattered range of locations that the particles would hit on the backside of the double slit experiment. So this showed that its journey was all these different possibilities, right? Like you said, the path integral formulation were all these different possibilities. And whereas with general relativity, and as you see in this first wave function, there's just one main possibility, whatever is the shortest distance to get from point A to point B. And so the reason that this is important, and we're applying this obviously to the macro scale, is if you can find a way to make the mathematics in both formulas work together in one combined formula, then we may be able to actually figure out, okay, if this is how quantum particles behave, then maybe this is how the early universe might have behaved, to actually find, it's like an elimination process to find out which, which path did our universe take either before the Big Bang or just after the Big Bang. So again, I know I just kind of tied it all into the bigger picture, but with this, that's what's so great, and why wave functions are being looked at on a topic like this specifically, because obviously there's wave functions of everything. And so I think that with trying to look at the cosmological scale, but on a quantum scale, so quantum cosmology is very, very important in something like this to figure out just what happened before the Big Bang.
Yeah, I like that you tie it all together, because the no boundary kind of does treat the universe as a quantum object. And I think it was Dr. Kroon I was telling before. I was talking about what's called a principle of supervenience that's in philosophy. And the principle of supervenience is basically that lower things affect higher structures. So even the smallest things will seem to be able to have very similar things as you go higher up. And so these waveforms and wave functions and probabilities, even though they only happen at the quantum level, do have macroscopic analogies in some ways.
Yes.
So, and you can talk about matter waves and things of that nature. So, but anybody else want to add on this one? Or is that kind of just a very basic way of looking at wave functions?
Good fun.
So
good.
I'm going to
yes, good.
I'm going to resist the urge to go down the double slit experiment rabbit hole, because that's a whole talk.
We could do a whole presentation on that, couldn't we?
Yeah.
I,
Oh man, I
I
keep
love
bringing
the
up.
double split. Yeah, the double
It's so
split's
good.
awesome.
And as I
Yeah, no,
say,
that would be fun. We could do something like that.
the triple split experiment and multiple split experiments. Actually, it's one of Feynman's
I think
early recording talking about asking questions about that.
Well, have you seen the triple experiment where they have a photon goes in one, goes back through it in the middle, and comes out the other, basically?
I did not
It's
see this.
bizarre.
Oh,
It's
I gotta look
bizarre.
this up.
It's really bizarre. The path that it took corresponds to basically going through one, coming through back through the middle, and then going out the other one. It's really strange. But
sounds like a crazy Saturday night right there.
Yeah, weird things happen in quantum. Again, not what you would expect in the macro thing, but again, even in mathematics, you can have weird things happen, like the Tarski paradox. So you can have like one thing form two. But anyways, that's gonna be on tangent. Next slide. By the way, it took some effort to try to distill this stuff down to the most basal way of explaining it. So I hope I'm not like making it too simple, but at the same time, I'm hoping I'm not going over everybody's head because like just basal approach, just basics, just the bare minimum to understand wave functions, right? I don't know how much more simple I could have made that.
I like it. I
this is
think you
great.
did a great job. Yeah.
Okay. Because it's not easy. It's not easy taking and distilling a bunch of stuff down. I mean, we all had wave mechanics. Wave mechanics is not easy. Okay, it sucks. And to try to get wave functions down, to explain how the angular momentum and propagation and phase and velocity and all that stuff, it's confusing. And so I had to what's the most easiest way to explain this? All right, so we're going to talk about real quick the normalization of a wave function. Because again, I think that if you go look at the no boundary proposal and something like that, you kind of need to understand how you do a normalization of a wave function. And basically, normalization is basically the wave function with respect to the position and time. If you look at the psi xt, that's a function. Whenever you see like f of x, it's a function of f of x. So this it's a wave function with respect to position and time. And the wave function normalization accepts the fact that a probability must exist between 0 and 1 at any given point, such that the total probability of the system is 1 that the particle does exist somewhere. So if you look at that wave function in the prior screen, where you had like the single amplitude of the sine wave, this single half of it, between the intercept on the y-x-axis, the first one and the second one, there's a probability of 1 that the particle is in that area. It has to exist somewhere in there. Now, at each point in there, it's a probability anywhere between 0 and 1. But the total summation, and you could use the normalization integral, which is basically just saying on an integral from negative infinity to infinity, with the probability density, right? The whole wavelength of the density of these particles has to be equal to 1. And so you're just normalizing it to 1. That's what it basically means to normalize it to me. And there's other normalizations out there too that Dr. Kroon could probably get into as far as eliminating infinities, but I think that's kind of way more complicated than we need to get into. But would you say that this is basically just a simple way of saying that we want everything to equal to 1 to normalize it?
You guys have
things
to be
that
really
exist
careful.
have a probability of existing of 1.
Yes. Dr. Kroon, what were you saying?
Yeah. You guys have to be real careful. If you're going down a sketchy part of the neighborhood at night, you go down a back alley and there's a guy in a trench coat that goes, "Psst, you want a probability density function? I got it real cheap." You're going to get ripped off because he's going to give you a non-normalized probability distribution function. It's useless unless it's normalized. So you got to be careful for people.
So this is why I'm trying to relate to people. These things only really kind of have use to us if we can normalize them. And so I wanted to think of a way. What's the easiest way to try to relate normalization? And I thought the normalization integral that I put here is probably the most simplistic way of doing it. And Landon, you're the math guy. Make sense?
Yes.
I mean, I got this formula from somewhere. Obviously, I didn't make it up.
Given the probabilities of over all space and time, you sum up all the probabilities for something that exists, you'll get 1.
Yeah. So I saw this formula.
In
I thought this
Edgar's
was the easiest
universe,
way
a
to
3.
describe it. Yeah. Unlike some that positing supernatural probabilities out there, you know who you are. They don't exist. There's no such thing. Yeah, you have to have. It has to be 1 to 0. So, anyway, that's your range.
Yep.
Okay, next. Now we get into some fun stuff. Like I said, there will be math involved. It's not that complicated. This is like high school stuff. So, basically, how does this all relate to this question? The distance formula in two-dimensional Euclidean space is basically derived from the Pythagorean theorem. We all learned this: a squared plus b equals b squared plus c squared. Now you can kind of manipulate that formula, and you kind of get d is equal to the square root of the square of the distance between two points on the x-axis plus the distance between 2 points on the y-axis, or the difference, I should say. So I could basically make a vector here, and a vector is basically a direction with a magnitude. So how far you want to go in what direction? That's a vector.
SQR means square root in this case.
Yeah, SQR is square root. I didn't want to do a square root symbol, so I used the actual SQR. But for 3D space, you can actually transform it a little bit, and you could do it with z-axis. So as you guys know, on a two-dimensional Cartesian plane, you have x and y, but in three-dimensional space, you got x, y, and z. So this is the distance formula. So if I want to figure out what's the distance between two positions in space, this is what I would use: non-Euclidean. Euclidean. So this is not for a non-Euclidean space, because obviously, as Landon pointed out, with Euclidean space, you have curvature, and so you have to take that into account, because you're not going to have a straight line in free space. You're going to have a curve. All spaces, there's no such thing as two parallel lines in non-Euclidean space, because they eventually curve at some point. Okay. Next slide. I think we need to kind of go into that at all, unless you guys have anything to add to that.
No.
Very basic. All right. This is where it gets interesting, and this is, I think, one of the cruxes of why using the no boundary proposal uses very advanced techniques, but is not really explaining what happens before the Big Bang, or maybe even what happens at t equals 0. How this works with the Hawking state is it uses what's called imaginary time. So normally for a four-dimensional manifold, you add in time, so you have the d squared equals x squared plus y squared plus z squared minus t squared. Okay, so that's how you would relate distance in space-time. So d squared is some interval in space-time, but that uses real time, and that's incompatible with general relativity at t equals 0, because we already established at t equals 0 general relativity doesn't work. So what they try to do is they rewrite t squared using just a little bit of math, where I is equal to the square root of -1. You guys remember? I'm talking about the audience, by the way, not you three, the audience. He's one of the best mathematicians in the world. I'm explaining imaginary numbers to him. Okay, but basically, to the audience, I is equal to the square root of -1. It's kind of a misnomer. People always tell me they really hate the fact they call it imaginary numbers, because they exist in the same way real numbers exist, but they're just on a different plane. And so, or a different field. Is it a different field or a different? It's a different field, they call it, right? I get field and ring mixed up. Landon, I would complex field.
Yes.
Okay. I'm gonna call it the complex plane. That's simpler. So
it's okay to say complex plane. We
yeah, I'm gonna say complex plane, because that's the way I remember learning it mostly. Like if you have a Riemann sphere, that's gonna be on the complex plane, and so you have a complex infinity at the North Pole of the Riemann sphere. So I kind of related it to a plane, right? These fields and rings and groups and all that ring theory stuff that gets way more complicated than I'll ever hope to understand. But what it does is it basically just takes the formula and puts it positive. So you have t squared, which is a positive value, which doesn't break down to t equals 0, but you're using imaginary time to do this, right? So what does that mean to have imaginary time? Do we actually exist in imaginary time? Well, I don't know. That's where I have to say, well, is it really modeling reality if it's dealing with imaginary stuff? Somewhat. I mean, complex numbers do model reality in sense of rotation, I guess, but I mean, how do you guys look at this when you're dealing with imaginary times to relate to t equals 0? And I am going to ask Athena on this only for the fact like she did a very specific video on no boundary condition. How do you kind of look at the way that Hawking took the no boundary proposal and said, okay, I'm going to use imaginary time to kind of get to the base of the shuttlecock, they call it, the shape that the inflation period made after it came out from that initial t equals 0?
Yeah, so looking at it as imaginary time is trying to make a parallel mirror to what a time is here. So rather than being on a complex plane, when it comes to obviously I'm using imaginary numbers, trying to obviously like saying that there is actual existence, saying that there is as if everything is still constant as it is now, it would be just as constant as it is there. And that's the whole purpose, is to try and create a parallel understanding of what we have now, and then try to just repeat that, but by using, you know, I guess imaginary time, as you're saying, because it's going to be t equals, trying to reach t equals 0, where the equation can actually withstand, and general relativity will not completely fall apart. So it is trying to make it in a sense where like things are exactly as they are now. Physics is still withstanding as it is now, and just looking at it from just a different using imaginary numbers. So exactly what you said is it's not that we're trying to say that like, no, we don't exist, none of this is actually in existence, because the whole purpose is to try and find a way that it'll work in this realm, so in this complex plane, and then, you know, try and make it as replicable to today, like I guess real standards, so real time standards, as opposed to imaginary time. So all the variables are supposed to be directly relevant to our universe as it is today. So that's from my understanding of the no boundary proposal and what Hawking was working on. That is the sole purpose. So as far as you asking about whether or not this was supposed to be, you know, the same conditions in which we are in today, it is supposed to be withstanding in both realms, if we can say. I guess that might be a relatively okay term to use right now, because it's all the same variables. You're just using imaginary time. So yeah.
There you go. Okay, that exactly the way I look at it. Dr. Kroon, you want to like touch on that?
Well, the only thing I'd say is, well, so Steve, this is getting into a topic that you like a lot, which is like philosophy and, you know, epistemology and stuff. Like, is it real or not? Well, of course, it's non-real in the sense that the term we use is imaginary, but is it reflected in reality and like in a real quote sense? I don't know. I like I said before, I'm a scientific
It kind of dives into
rationalist.
more philosophy at that point, right?
Yeah, they're definitely useful for solving differential equations, and they show up a lot in you know, solving circuit problems and quantum mechanics. It's all over the place. So I don't know. They're definitely useful, and so I guess by my existence and my usage of them, they have a little bit of realness to them in that sense, in that instrumentalist sense.
In the instrumentalist sense, sure. Landon?
Yeah.
I mean, don't confuse the model with reality.
Right.
This is a good model for describing reality. Whether reality works this way or not is perhaps irrelevant to the value of the model, which is helping you describe what you are observing reality.
Mm-hmm.
Okay. Next slide. Okay, so what does this all mean? So in order to even try to express what happens at t equals 0, or even understand any of this, you got to know a hell of a lot of shit. Let's be honest. This is not easy stuff. To even approach the question, what happens before the Big Bang? Yeah, it's nothing that you're going to dive right into without having some kind of basic understanding of a lot of different complex topics. It's combining mathematics, it's combining cosmogony, it's combining physics, it's combining mathematics. A whole bunch of different subjects are required to even start to approach something of this magnitude. It requires very complex normalization techniques, and they are very complicated. Dr. Kroon can attest to that, I'm sure. The use of imaginary time, and to even attempt to describe what happens at t equals 0. So my overall point of this is to kind of give everybody, whoever wants to look into this, these are the things that you kind of need to look into if you're going to really understand Hawking's no boundary proposal, and what it means to even ask the question, what happened before the Big Bang, because there is literally no real time at t equals 0. So there cannot be anything before t equals 0. So to ask the question, to me, it's still nonsensical, because you're dealing with now imaginary time to even get it at t0. Now, Landon had brought up things like the bounce, big bounce, and the multiverse, which kind of gets into things like meta time and other things, but they're not what we're talking about as far as time in our universe. So I'm going to maintain that while it's productive to ask the question, what happened before the Big Bang, it's still a nonsensical question. Again, if I asked you, point to me on the real number line where the imaginary number is one, where I exist, it's nonsensical. But is it a productive question, maybe from a pedagogical approach, by saying, hey, look, it's not on that line. I'm showing you that's not on there. So is there educational value out of it? Sure. But it doesn't make sense to really attempt to legitimately ask that question when it's a nonsensical question. That's my summation. I think is that my last slide, Dave? Okay, one next one. And then you guys can do your summations. It doesn't get you to before the Big Bang. It cannot be used to describe conditions at t less than 0, because there is no space, there's no time, imaginary and otherwise, to measure. There's just, I'm going to say nothing now. It gets into philosophy whether there's nothing before the Big Bang, because again, there's just a nonsensical statement there. So I don't really want to say there's nothing before the Big Bang. I think the whole statement is nonsensical. But Stephen Hawking's attempt to describe t equals 0, what we know now as the no boundary proposal, simply does not get you to anything, quote unquote, before the Big Bang. And also, I did want to note this: it assumes Lorentzian over Minkowski space, which I think is a big thing. Now, that's just my view from reading into this. I'm really just pulling that out of my particular interpretation of this, that we don't use a Lorentzian or neo-Lorentzian model. We do use a Minkowski space model. So it takes a very different approach to how we look at space-time and how we look at spatial dimensions with relationship to emergent temporal dimensions. But I think now this one's the last slide, right? Dave, is that the last one?
No.
And then you guys can wrap up. How many more I got? Oh, okay. Okay, I remember now. I was like, wait a minute.
This one and 2 more, Steve.
These are quotes. Okay, so let's just rush through this because we're running out of time, and then you guys give your summations. In Stephen Hawking's own words, events before the Big Bang are simply not defined because there's no way one can measure what happened at them. Since events before the Big Bang have no observational consequences, one may as well cut them out of the theory and say that time began at the Big Bang rather than anything before the Big Bang. So that's in his own words. Next one. He also wrote in A Brief History of Time, as we can see, the concept of time has no meaning before the beginning of the universe. And one could still imagine that God created the universe at the instant of the Big Bang, or even afterwards, in such a way as to make it look as though there had been a Big Bang. But it would be meaningless to suppose that it had been created before the Big Bang. And I think Landon kind of touched on this, and it does get into more theology and philosophy. If some entity exists out space-time, how did he create something in time? It makes no sense to say that there was a time before the universe such that something existed and that created all this. It's a very difficult. I don't think it makes much sense for a non-temporal entity to make something that's temporal. But that's my position on it. And we can get into quantum foam. We can get into how the bubble expanded, and you kind of did a little bit earlier, but that's not a being doing that. It's not a non-temporal being doing that. So next. And the end. So the question of what happened before the Big Bang is nonsensical. That's my summation. So let's kind of get your guys' view on this. Let's wrap it up. I don't want to keep it too much longer. Athena, I'm going to save you for last, if I may, because you're new, and I'm going to give you the longest thing that you need to do to wrap up and make sure that people do subscribe to you. So I'm going to actually start with my co-host first, Landon. What do you got to say about the presentation?
Well,
did I change your mind
at
all,
again,
or
Steve. I thought it was a very good presentation.
Thank you.
And
it
allowed us to bring up a lot of topics. You can find that these topics are all very tightly interconnected, right? And it's difficult to talk about one thing without bringing in a number of other items. I would encourage people to again consider that models. Don't confuse models with reality. Models are what we use to try to describe reality. And the mathematics behind those models helps us give very precise language as to what the model is. In regards to the question about, what happened before the Big Bang, there are valid Big Bang models that say that state that time was created at the moment of Big Bang. That is t equals 0 was where time was created. If you talk about time being as far as causality, as Hawking eloquently stated, if there are things that happen before t equals 0, they have no effect on what happens at t equals 0 or beyond. And so, or I should say, certainly beyond t0, they may have an effect on at t0. If that is indeed the case,
can I interject real quick? One possible
Sure.
exception. If there was no actual t equals 0 such that there was anything before, like there's a paper that I was sent, and I think I don't know who sent it to me. It was maybe Dr. Kroon sent it to me, but I was reading a paper on the Big Bounce where there is a small window where any prior existing universe of some kind could have had a minor influence on the initial conditions for our universe as of today. So it was
that's why I admitted my. But that's why
did you send that to me, or did
he?
I don't remember. Who sent that to me?
I don't think I sent it.
I don't know. I've been talking to a lot of people on this particular topic. So, but on the Big Bounce, there's some, like you said, it doesn't get to t equals 0 because there's no mathematical singularity in that particular model, right?
Yes.
Like in this model, there's no singularity.
And so you can either say that you use a model that says that time was created at t equals 0 in the Big Bang, or that things that are t less than 0 before the Big Bang have no impact on things after the Big Bang, no consequences, and therefore, as Hawking said, you might as well not cut them out of the theory.
Okay.
They have no
Dr.
impact. So it's a valid thing to wonder, but but not all questions have answers, and this may be one of those questions that is actually not valid, and the universe doesn't have an answer for.
Yeah, no, I agree with that. That's why it wouldn't be before the Big Bang. That's why. I mean, no matter what theory of time you subscribe to, A or B, it doesn't have any effect here. You don't. If there's a multiverse or something like that, it's not before the Big Bang. It's not with respect to us. So you can't say before. It gets into a lot more complexity that I'm willing to get into at this particular junction. But yeah, it's not before the Big Bang. But Dr. Kroon, what say you?
So when someone asks what happened before the Big Bang, the answer is not even nothing. There was no before.
Right. That's what I said before. I don't even like these phrase. There was nothing before the Big Bang because again, it's just a nonsensical question to me. But let's kind of wrap it up here, Dr. Kroon.
Yeah. I mean, I agree with everything Landon said, and that's a good position to take if I understand correctly. But
yeah, you always want to agree with Landon for the most part, unless it's philosophy. Then you feel free to go after him.
Yeah, we have learned a lot, and the royal we. And we provided a rather broad and comprehensive presentation of the background that one would need to investigate further, to even begin to understand things as complex, and no pun intended, as the singularity or the exact moment that the Big Bang started, when it was at t equals 0. And so we've opened up a broad spectrum of concepts that we could conceivably use in current and future research to inform our studies of the universe at large and its origins. And so, in that sense, I'm I guess, an instrumentalist and a pragmatist and just an all-around science guy. And so, yeah, the bottom line is we got to tell Kyle that the answer is no, it's nonsensical. And just like saying what's colder than absolute 0 or what's north of the North Pole or south of the South Pole. But you could have a lot of fun talking about it. And that's all
I
have
think
to
that's a
say.
good way of wrapping it up. And maybe one of these days we'll get into the whole what happens at absolute zero, and even you can kind of go lower than absolute zero, but it's actually warmer than absolute zero. It's weird what happens right at absolute zero. Some of the effects.
Yeah,
that
because
occur.
it's trying to
Yeah,
pull
because
it
you have
back.
negative flow, right? So
Mhm.
absolute zero is absolute zero, but there is small things that you can actually mess with to get it to go less than absolute zero, but it's actually a warmer system, and heat always goes from warmer to colder. So, but that's a whole different ballgame too. But anyways, Athena, first of all, I do really want to thank you for coming on here. I know that you know, I don't know how often you do things like this. I've never seen you do any kind of on-air or interview or anything like that, so I'm very appreciative of that. I just happen to like your videos, and especially that one because it was so on point with what we were talking today, and I do hope that we can kind of coax you to come back. We have NonSequitur show. We have my own channel that we have to do things on, and we talk about science a lot, so I can add you to our list. When we have hangouts, you'll know about it, and you have free reign to come in and drop in on any of them. But what do you think so far, and what's your summation? And please tell them again how to find your stuff, and because I'm getting people your links, but they got to go subscribe to you guys. What's wrong with you? She's a supermodel and she's brilliant. What the hell's wrong with you? I mean, come on.
Well, you're
What's
the
up?
best. This was so much fun. I definitely would love to come back and talk about some more stuff, like the double slit experiment. So, well, my overall gist from everything we spoke about today is the fact that we haven't collected any data from before the Big Bang happened would answer, my answer would be, yeah, it's a nonsensical question to ask if there was anything before the Big Bang, because there's no observational data. But part of me starts to think about things that we don't understand, which is if there's alternate dimensions happening that we can't access, or something like certain animals that can't see color, but we know color exists. So moments like that make me think, maybe asking if there was anything before the Big Bang isn't really nonsense, you know? So that's kind of where I'm at right now, but I think it's good to keep exploring this. I mean, it's kind of silly to say, but I'd love to obviously pick everyone's brains about that another time. But as far as what we do understand with math and the fact that there is no measurement of time or anything existing, any type of thing existing before t equals 0, then it would answer, the answer would be that, yeah, I mean, it's a kind of a nonsensical question to ask. So that's my overall summation. Yeah.
So I'm going to ask you a question, since you're involved in education, science education.
Yes.
What do you do when a kid comes up and says, doctor, what happened before the Big Bang? How do you respond to that child's question?
So I usually will say to them that right now we don't actually know. I usually will say we don't actually know, but we do know that there is an entire process that happened just after the Big Bang. So I encourage you to go into this field, to try and figure it out, to be part of all the teams, to research what Stephen Hawking was researching before he passed away, and try and come up with your own theory. That's usually what I'll do.
Excellent answer.
It is an excellent answer. So I'm gonna leave you with one last question, and this is gonna be a real quick one, and then Dave's gonna take us out. And by the way, stick around for a few minutes just afterwards if you can. So here's my question to you all, and what do you think? So Landon, do colors exist? And the correct answer is no. I'm gonna tell you right here now. I'm just gonna be, poison the well. But do colors exist, or is color realism a thing? Color irrealism.
I say perceptions of colors exist.
Why do you got to change the question, Landon? Do colors exist other than phenomenally in the brain? Do they exist ontologically in the universe? I can play this game too, trust me. Why does he got to think about this question?
Or I could just stop the whole thing now, Steve.
Yeah, come on.
I mean, okay, so Steve, you're claiming that colors don't exist.
We're gonna have a chat, Landon. I'm gonna. You know what? You know me. I don't care if people have PhDs. If I have a good argument, I'm gonna lay it out there. So we're gonna get back to you on that one.
So I'm thinking about.
And now he wants to answer.
I'm thinking about your question. The reason why I'm thinking about your question is that if you don't understand how complex the question is that you're asking, you don't understand the question.
Well, that's why it is a complex question. It very much so is. But that's why I'm actually narrowing it down. And I'll even phrase it this way: do colors exist other than just existing in your mind as a phenomenon that exists because of your brain's interpretation of the light being reflected or emitted from an object? Or is there an intrinsic property of colors that exist independent of our observations?
I would speculate that they do not exist independent of our observation.
Good answer. Good answer. What about you, Dr. Kroon?
So I always like to define the terms of the question before answering it, so I know what I'm
Got
answering.
too many smart people in here.
And so I could say if you interpret color as an intrinsic property of the photon that's quantified via its wavelength, then we don't need to perceive it for it to exist. But then, playing devil's advocate, you could turn right around and say, "Oh, that's wavelength, that's not color." And now we're into
that's
semantics.
not phenomenon. Yeah, the color itself only in the brain.
So
that's not actually semantics. That's actually phenomenology.
Okay. Yeah, but it undermines the possibility of perception, and so I would say yes, the colors exist.
We're gonna have a talk.
Yeah.
Athena, how about you? Are you gonna side with them? Or are you gonna go with me on this one?
Yes, colors
By the
exist.
way,
That's all I'm gonna say.
You know what?
Can I change?
I don't mind.
Okay,
I don't mind. I'll do it. You know I will.
Steve, actually,
I got Dave on
thinking
my
about
side.
the
Dave,
way
please tell me
you're-
hey God, are you on my side? Dave?
Well, because Steve, you can't.
Steve.
He's
The
ignoring me.
only
Why is
color-
God not listening to me?
The only color I know for sure exists is purple. Just saying.
Purple's the one color that definitely doesn't exist. Even color realists say purple.
So I think hearing you ask the question, people
Purple and
discuss
pink. I
it.
don't remember. All right,
Steve,
next
I
time,
think
guys,
The
we're gonna talk
answer
about
to
color.
your question that I think you're asking is no. It does not exist outside of the mind.
Right.
Right. That's the question I'm asking. Yes.
Right.
All right,
Which
so
is
that's where
like
you
how I'm
agree on.
interpreting it as well, but it bothers me. We'll have to
Well,
make a
here's
debate about
another
that
question,
sometime.
Steve. Does the fact that we perceive it make it real?
Exactly. That's what I would have brought up.
No, because we perceive dreams, but dreams are not real either.
Dreams happen.
Well, the
I know they
colors.
happen.
The color.
Well,
if you want to, see, here's the way I look at it. If you want to say that the color is because the brain's interpretation of the photon's energy positing energy on the retina, okay. But the problem with that is it doesn't hold, because in a dream there's nothing hitting your retina and we still see colors. It's a phenomenon that exists solely in the brain because the brain is interpreting electrical signals, and the way the brain does that is by producing a color that we have a phenomenon that exists, a phenomenology.
Wait, then where's the malfunction for those that are colorblind? Is that in the brain or is it in the eye? I don't actually know this, because then that would bring up an argument.
Well, the colorblind people, obviously they don't have the cone to see certain colors, right? Or there's some kind of physical damage, right? I don't know if they dream in color. You know what? I have no idea. That's a good question.
I know my neighbor is colorblind, and he's been a friend of mine for like 2 years, and he says that he doesn't notice anything different between, because that would favor
I would think that you could still
neurological standpoint.
Right. I would look at it this way, and we can check this out, and we're going to be ending this in like 30 seconds. But I would look at it this way: if a person has been exposed to colors before, then their brain can interpret certain colors, and they know that what's supposed to look like. Because the brain is really good at filling in the blanks. So even though you can't visually see colors anymore, if you lost your sightness, then you wouldn't see a particular color. But if you're colorblind from birth, then I don't think that it's possible that you could see like the color green, because you know no reference to what green actually looks like. Do you?
Mm-hmm.
So
seems like a rational approach to me.
I was in a medically induced state of keeping me out of my mind, because I had an extremely high fever as a child, and in that medical state, I perceived and experienced a color that I knew didn't exist on the color wheel. I can still remember that color.
That's pretty cool.
But it doesn't exist.
Well,
right?
It
again, exists in my mind.
Purple. I think it's purple or pink doesn't exist either.
It's pink.
I can't
pink
show you this color because it's not. Yeah. There's no physical manifestations of it. It happens to be a drug-induced symptom in my brain.
And there's also people that are tetrachromatic. What are they? Tetrachromatic? Tetrachromograph?
Mm-hmm.
Yeah, they basically can see multiple colors that we can't see. But anyways, fascinating topic. We got so much more that we could discuss, but we'll leave this for other episodes. We are going to be trying to do this every other week, and if I get to every week, and I will, but I got to tell you, there's so many things going on. I am having a discussion coming up. I believe it's on the 8th of October with John Perry from Stated Clearly. I'm going to be talking about his DNA a code. I'm arguing that it's not a code; it's more like a cipher. And I'm going to be arguing from different reasonings for that. I've talked to Dr. Mays. I've talked to Dr. Stern from Johns Hopkins University. He's a geneticist. And I've also talked to another friend of mine who I just know by epigenetics on Twitter that you guys may know. He's a geneticist PhD. All three of them are in concordance with me. So I'm going to be using my particular arguments with addition of what they've told me and what I've read. And I'm going to be trying to explain it to John, who I have the utmost respect for. I love his videos, Stated Clearly. I just think that it's a little bit of a misnomer to call it a code, unless you're talking about specifically the lettering, in which case you're just substituting secondary symbols for primary symbols. But we'll get into all that. But if you guys got suggestions, please leave it for me in the comment section. Message me. Let me know what you think of these videos. Thumbs up, thumbs down, whatever. But definitely go subscribe to Athena. I put the link in the video description, and I've put it in the live chat like 4 dozen times. So I've already seen her numbers go up, but I want to see over the next couple of days. Let's get her at least 200 subs out of this, because she took her time out to do this, and I know she's got things to do here in about 15 minutes or so. So we got to wrap it up. So I want to thank you all for joining us today. Thank you for double streaming to my channel and the NonSequitur Show. The first time we've done that, and I thought it was fun. So thank you all. Dave, you can take us out.
Non sequitur. Your facts are uncoordinated.